Well, let's do another example to help remind ourselves of the way that derivatives work as far as from the perspective of tangent lines, right? And remember that whenever we take a derivative and evaluate it at a certain point, we are actually finding the slope of the line tangent to the curve at that point. So let's deal with it here. First things first, of course, if we're given y equals 2 sine of x, y equals 2 sine of x. What we're looking for is the line tangent to this curve at certain points, so we have to find dy dx. That's a dg. Good lord, that's not a very good y at all. Let's try that again. dy dx is what we're looking for, but of course we know by the constant multiple rule this is going to become 2 times the cosine of x. Well, so far so good, right? That's our derivative. So let's talk about how do we find the slope of a line tangent to a curve. Well, what we need is a slope and a point. Now, we've got our point. What we need is a slope. So let's deal with our slope here. We evaluate the derivative, dy dx, at the given x value. So we're going to evaluate this at x equals 5 pi over 6 and see what happens. So we're going to be taking 2 times the cosine of the angle 5 pi over 6. Well, at 5 pi over 6, our slope, or sorry, a value for cosine, what is that? That's a negative square root of 3 divided by 2. Since we're in the second quadrant, the reference angle of pi over 6 gives us a cosine of radical 3 over 2. And therefore, our slope for this line will be negative square root of 3. So what could we say about it? Well, let's use the point slope form. We would say that y minus 1, that's the y value given, is equal to negative square root of 3 times x minus the x value that's given in the point, and that's 5 pi over 6. Now, sure, we could go through and isolate y and put this in a nice point slope form, but I'll tell you a slope intercept form if we wanted to. I think I'm done with that. That's all I really want. All right, let's try it again. This time, let's use our other point over here that we're given, y equals pi over 2, comma 2, right? That's our x and y value right here. So evaluating our derivative at the point pi over 2, let's figure out what's going to happen. When we substitute in x equals pi over 2, it means we're going to be taking the cosine of that angle pi over 2, that equals cosine of pi over 2. And we know that the cosine of pi over 2 is equal to 0. So what does that mean? Well, I suppose that means if we have a slope of 0, we've got a horizontal line. If you recall the process here, horizontal lines are the kind of lines in which we write y equals some number. So the question is, what equation do we use? Well, what value do we use for y? Well, the one on the given point, right? In this case, the horizontal line will be y equals 2, which means we have a point where the slope is 0, and that's actually sort of interesting to us, right? Because we would note that if we were to actually look at the graph, and let me make a graph for you. Here it is. What are we looking at? Well, in our line right here in blue, y equals pi over 2, right? Here we are. This is that point. We have a nice horizontal line through that point, right? Because that's a point where the slope is 0, right? Well, there are other points where that's true too. Let's see. Also, we might say, well, the horizontal line here, this line, y equals negative square root of 3, that was at 5 pi over 6. And that line, if we were to look at it actually, is something a bit more like this. We know that, here we are, at y equals 1, right? At y equals 1, that's a point where we have a slope that's negative square root of 3. So this line right here was our other slope. So we're pretty good. Pretty good.